Okay, so this week we're going into macromolecule prediction, structure prediction, and protein prediction, then layer RNA prediction, structure prediction, things like that. So the first lecture in this, I asked Roy Campbell to come over and talk a little bit because he does a lot of stuff in protein structure prediction, and so that I'm going to turn the time over to him. Thank you.
Just a little background. Why is Campbell interested in protein? Well, my training is in theoretical nuclear physics, and I worked for a while on interactions between protons and neutrons. And from the quark structure of protons and neutrons. And there's one technique used to study protons and neutrons at the level of the fundamental theory, and that is something called lattice quantum chromodynamics. Sounds daunting, does it? It is. But as I was trying to get a handle on lattice calculations for proteins, I ran across, just doing an internet search, lattice proteins, toy models of proteins, where the amino acid residues can reside at the corner or at the corner of a grid of squares, and so it could only fold into a shape on a cubic lattice or even a square lattice. So it was sort of a toy model of protein folding, and they only had two kinds of residues, and they were trying to understand folding pathways and so forth. So I got really interested in that problem and have been working off and on it ever since. For a while I was particularly interested in protein structure prediction, but recently I've been working on techniques for calculating not just the final structure of the protein, of the folded protein, the native structure, but the folding pathway. How does it go from an unfolded state to a folded state? I think that's important. Because, for example, there are diseases associated with just the misfolding of what would be a perfectly healthy protein, and it just misfolds. So that has something to do with the folding pathway. I want to just talk about structure prediction now. Of course, the protein folding problem is simple in its statement. Given an amino acid sequence, such as this sequence for trypsin, predict the folded structure of the protein. Pretty simple way of stating the problem. And of course, this is the cartoon model or representation of the protein. And get a better idea, a different view. Here's the base building version of the protein. So that's the problem. Now, that problem's been around a while. I mean, ever since the discovery of the alpha helix, people have been trying to piece together protein structure. With the big breakthrough, of course, was related to the unraveling the structure of DNA, because then it was realized that X-ray crystallography could be used to study these molecular structures. And of course, you all know about the protein database, PDB?
I've not talked about that yet.
Okay, well, it's a collection of all the known structures that people want to make public, all the known protein structures that are known, and I think by now there are over 80,000 structures. But when it first started in the 1960s, the protein database started with 7 structures. Those are all that were known back in the 1960s, 7 structures. And there was actually, I found this beautiful book. I should have bought it, but I didn't. At Powell's in Portland. We were just talking about what we like about Seattle and Portland. At Powell's Books in Portland, it was a book of protein structures. And all the known structures at the time this book was published were in this book. And there were these beautiful hand drawings of these proteins. There were about a dozen of them. And it was a real beautiful thing. Of course, when the World Wide Web was first invented, someone tried to publish someone did publish a book with all the known websites in it. list of websites categorized, but of course that would be impossible now. In any case, the problem's been around for quite a while. When I was a kid, my parents gave me this book. It's a golden book, you know, not golden books, right? It's a deluxe golden book, published in 1958, called The World of Science, and I love this book. See, I'm kind of beat up here. And in this book is this picture of an alpha helix, and the discoverer of the alpha helix, Linus Pauling, right here. And I love building models. And I thought, how do they know this? How do they know that complicated molecule has this structure? I thought that was a great question. And in the text associated with this question, there was a paragraph called Folding the Chain, and it talked about predicting the structures. And here's what it said. What we need mostly, says a chemist with a smile, and here he is sitting by his computer, okay, 1950s version computer. What we need is luck and calculating machines. So they needed computers. And of course, this is a computational biology class, so you understand now that with this amazing, powerful computers, biology is, in some sense, going through a revolution. Yeah. Right now, I'd make a rude comment about biology. I was going to say, and becoming a real science. No, sorry. Okay, so I'm going to try to talk about at least two structure prediction methods. Here's a list of 4. Some of them are very closely related to each other, and all of them really come down to assembling fragments of sequences with known structure. Assembling fragments of sequences with known structure. Basically, that's what they all come down to. There's homology modeling, fold recognition, and protein threading. This is a really cool name, protein threading, because you can actually imagine taking a wire the shape of a known protein and threading the amino acids onto it like beads. It's an apt name for that procedure. And then ab initio structure prediction, where ab initio means from first principles, and that's the first method I want to talk about. So here's a structure prediction flowchart. You start with your protein sequence, and then you try to determine if there are similar sequences with known structures. Similar sequences with known structures. How similar? Well, whether the method you choose depends on the degree of similarity between your sequence and known sequence. So you run BLAST or SciBLAST, study BLAST, SciBLAST, and find a similar sequence. Okay. Is it similar? The word uses, is it a homologue? Is it similar sequence? What's homologue mean, really, in biology? Homologue means similar structure, but that's interpreted to be that it's evolutionarily related. Those structures are evolutionarily related to each other, but they're similar structures. Just as my friend here is 96.4% orangutan. So some of your proteins would be homologous to some orangutan proteins. Okay. So you see, if a homologue exists, then you could do homology modeling and get a candidate, a model. Keep in mind, these are models, these are candidates, these are theoretical predictions. Okay, avoid saying this is the structure, avoid that at all costs. It's a candidate structure. And until the actual structure can be measured experimentally. It's important to have that, but keep in mind it is just a model. It's just a model. All right, if no homologue exists, then you can see if some segments, are there regions in the target sequence that are similar to other regions without necessarily wide-ranging similarity. If there is, then you can do protein threading, and not only do the protein threading, but include interactions between the amino acids. Once you string them on the thread, then you can revise the structure by taking pairwise interactions between the amino acids. All right, if there's no known folds, then your last choice is ab initio structure prediction. Okay? Well, let me show you an example that I ran. I ran this on a server that's on the internet called Robetta. Robetta. Okay, you can submit sequences to Robetta, and it will do an ab initio structure prediction for you. The last time I submitted a job to Robetta, it took over a month for the results to come back. So there's quite a bit of turnaround time. If you had a lot of structure predictions, then you can get the software, Rosetta, which is something you can install on your own machine or cluster of machines and run them in-house. It's kind of interesting. You can get the Rosetta suite of programs from the University of Washington. If you're an academic institution and promise not to use their software for profit, you can get it for nothing. But you have to promise that you're not going to use it for profit. In fact, you have to get an officer of the university to say, no, we're not going to use this for profit. I did that, and when I downloaded Rosetta, and I took it to the academic vice president, one of the university officers, and she said, is it okay for me to sign this? I said, sure, sign it. So she signed it. We had a copy and ran it in-house for a while. If you're a company like Pfizer or a drug company that wants to do structure prediction, you can license the software for $60,000 a year. Racket. Anyway, this is like robotic Rosetta. It's an automatic. It runs the structure prediction automatically, but it does take quite a while. I think one reason is that there's a long queue of people submitting jobs, and if you can apply to get high priority on Robetta. Okay, in which case when you submit a job, it'll be moved near the front of the queue. Otherwise, if you're just some guy in Yakima submitting a structure prediction job, people like to do this all the time, right? Submit structure prediction jobs. Website. Then it goes to the back of the queue, and I think that's why it took so long. All right, so here's the job. Some of you may have seen these genes before, these proteins. LMCA and LMCB, anyone heard of those? Okay, if you've worked with David Lindsay, you've probably seen the proteins before. Here's a sequence for LMCA. There are two genes in dictyostelium. They're almost identical copies of each other, except there are two mutations. Here we have, from LMCB, we have glutamic acid here. We have valine substituted for glutamic acid, and valine substituted for isoleucine here. So there are only two different. The reason I was interested in this was because Dr. Lindsay extent that when one of these is expressed, well, the theory was that when one of these was expressed in dictyostelium, everything happened normally. When the other one was expressed, then it didn't make the growth to development, growth to development transition. Okay, that was interesting. How could that happen with only 2 mutations? Well, they must be important. The isoleucine to valine is a conserved mutation. The glutamic acid to valine is non-conserved. So that's, if there's a functional difference between these 2 mutants, then it probably has something to do with the substitution. I mean, after all, you know, they're diseases that are caused by single point mutations, right? What's a famous disease caused by a single point mutation? Sickle cell disease, right? Sickle cell disease. And it happens to be glutamic acid to valine substitution that causes sickle cell disease. So that was interesting. All right. So after running both of these jobs on Robetta, here are the results. Here is the LMCA and here's the LMCP. Here are the sites where the residues are different. And you may notice that here, where we substituted valine for isoleucine, the structure is very similar. We have this alpha helix here, that's intact. We have an alpha helix here, that's intact. We have a very small fragment of an alpha helix here, that's intact. So it looks like the structure hasn't changed much around that conserved mutation. But here, on the non-conserved mutation, we see that this whole alpha helix is unraveled here, or rather, not unraveled, I'm sorry, it's moved. Now we have these 2 alpha helices here, parallel to each other, and here they're at right angles to each other. So it looks like the structure in the vicinity of the non-conserved mutation has changed dramatically. I took this, I actually went over to see the leader of the Rosetta group at Washington State University, David Baker. And I talked about this result, and he was surprised. He said, you need to be very careful because Rosetta wasn't designed to find these subtle structure changes due to single point mutations. Most of the time when you have single point mutations, you don't get big structure differences. And he said just finding this big structure difference due to the single mutation is, you need to be very careful because Rosetta wasn't designed to find that. So the next thing to do would be to revise this structure. I haven't done this yet, but if I was still going to work on this, the next thing to do would be to revise this structure using molecular dynamics code to actually see if, when you calculate all of the interactions between all of the atoms and try to minimize the Gibbs free energy of this molecule, if the structure changes. Okay? Because one of the things that are typically done on these ab initio calculations is that once you have the predicted structure using the fragment substitution, then you can run molecular dynamics simulation and see if the structure will find a lower energy solution. Okay, it's revising the structure. So that would be the next thing to do. Does anyone want to do that? Let me know if you want to work on that. All right, just as an aside here, you can not only use the computer to calculate predict structures, but you can also try to predict active sites. Active site prediction. There's a program called Thematics, Theoretical Microscopic Titration Curves, that will give you a prediction for active sites. And here's how it works. You imagine you put your structure, your model structure, or imagine putting it in a solution. Of course, all of these predictions have to occur in solution. Solution is very important, okay? Otherwise, you wouldn't get the hydrophobic, hydrophilic effect would be there if you didn't have a solution. Okay. So imagine putting your structure in a solution and varying the pH of the solution, okay? Vary the pH of the solution. Each of these lines represents a residue on the surface of the protein, the part of the protein that's in contact with the solution. As you vary the pH of the solution, the charge state of the residue will change. So it has to be a polar residue, and it'll change from 1 to 0. You get these typical transitions as the pH changes. The charge state goes from +1 to 0. Okay? And the position at which this occurred is the pH at which this occurs especially. Now, occasionally, got a transition that is an anomalous transition, meaning it's not like the others. And it's been shown by the authors of the thematics algorithm that it's typical for an active site to have two residues, two amino acid residues, two side chains that have anomalous behavior. All right? So if you get anomalous behavior for two side chains that are close to each other, that's a candidate active site. Wouldn't you like to be able to predict active sites? You can see what binds to it. That's really cool. All right, so this is the LMCA. This is the titration curve for LMCA. And you can see anomalous behavior for this residue. See, it doesn't make that nice smooth transition. It kind of jumps out at you. This is for asparagine 115. And this one is for tyrosine 180. Okay, so we have anomalous behavior for two of these amino acids. Am I saying that right? And here's what it looks like. Here is LMCA, and here are those two residues. Look, they're close to each other on the surface, so there's a candidate active site. Now, what happens to the candidate active site for LMCB? Well, it's very interesting. If you look at the LMCB structure, those side chains are buried, so it looks like the active site goes away. So maybe the effects at the cellular level have something to do with the active site on LMCA going away when you have a mutation on LMCB, maybe. Okay. So there's a clue. So the structure prediction, active site prediction has given us a clue as to what's happening. It helps us form hypothesis. Okay, as to the cause of the behavior of the cell when one of these is expressed. All right. Now, what would you do with that hypothesis? Well, you design an experiment to test it, right? We are, after all, remember, some of my students remember that call and response with my class. We are, after all. Yes. So we form theories and then we test it. Thank you very much. That is nostalgic for me. All right, back to Rosetta and structure prediction. David Baker is the lead of the Rosetta group at the University of Washington. Rosetta, and there are other ab initio programs out there. Rosetta is one that's been quite successful. Rosetta is a suite of programs, scripts, and files for modeling protein structure. It has been successful with CASP and Capri. What is CASP? Critical Assessment of Structure Prediction. These structure prediction guys have a really interesting game going. It's like the structure prediction Olympics. And they do it every other year. They run a CASP competition. I don't know if they have flags and they stand on little stands and give medals, but it's kind of cool that they have this competition. Every other year, they assemble a set of protein sequences that are for which the structure is going to be measured. In other words, there are labs that use X-ray crystallography and NMR to determine protein structures. And they tell the CAS people, we plan in the next year or two to measure the structure of this protein. And it hasn't been measured before. So that becomes a candidate. And they assemble these sequences, and then everyone that enters the competition tries to predict the structure. Okay? So they all submit their structures, and they have different categories, like the 100-yard dash, quarter mile, and stuff. They have different categories, like fully automated structure prediction with human intervention. In other words, as the process goes on, the researcher can go in and tweak the results. Okay, so they have different categories, and then everyone submits their structures, and then when the labs give their measured results, they score everyone's structure and see who's successful. They also do this with protein-protein interactions also. These programs that do structure prediction have also been adopted to calculate interactions between two proteins, very cool, and interactions between proteins and random molecules. So you can see why a company like Pfizer would be very interested in this technology. By the way, they've also extended this and are integrating Rosetta into a protein engineering program. In other words, given an amino acid sequence, find the structure, predicted structure. What they're doing in the protein engineering program is choosing a structure, saying, I want a protein with this structure. So far, they've only been able to do it with small proteins. But I want a protein with this structure. Then they use Rosetta to calculate an amino acid sequence. They say, this is the structure I want. They calculate the sequence that will give them that structure when it folds. Isn't that the coolest thing? Who would have guessed? I was just driving across the University of Washington campus the other day. My son lives within a few blocks. Driving across the campus, I noticed a new building there that had several departments in it, and one of them was protein engineering department. They had a whole department. I think if I was starting out again in science, I think I might go into something like protein engineering. Or maybe I'd just be a cowboy or a fireman, but that just seems like a really interesting technology that is just going to explode one way or another. So, and then they synthesize the protein. And they measure its structure and they compare it to what they're designed. So it's a very, very cool technology. So Rosetta has been used to design. All right, here are the basics. The basic theory is that, proteins are thought to collapse from an unfolded to a folded state. Could it be any other way? I guess you can think of other ways. But proteins are thought to collapse from an unfolded to a folded state. And that local conformations precede and guide global folding and tertiary structure. In other words, the theory is that secondary structures form first. The alpha helices form first, the beta strands form first, and then they interact with each other to form the tertiary structure. So here's how it might happen. We have an unfolded protein here in this cartoon. We have some secondary structures forming here. Here's an alpha helix forming, and then the alpha helices and the beta strand interact with each other to get the final folded structure. That's how the thing happens. What they start out with, Rosetta algorithm step 1, is they assemble fragment library generated for each query sequence. So they'll look at fragments, they'll chop, in other words, they'll take the query sequence and chop it up into segments, long segments of length 9 and shorter segments of length 3. And then they will go to the protein data bank, or they'll go to known structures and look for those same fragments, okay, in the protein data bank with known structures. They'll look for those same sequences, exact matches for those sequences, okay? And then they'll lift that structure from the protein data bank. That is, they'll have the sequence of, say, 3 amino acids, and they'll have a set of torsion angles and side chain angles, right? That's the structure. How's the structure represented? A set of torsion angles and side chain. That's the structure. So they have a sequence and they have a structure. They might find several copies of that sequence in the protein data bank. I mean, if you only have a sequence of 3, you're going to have a big library of candidates. So you have a library of 3 amino acids and their corresponding structures as found in the protein data bank. I maybe misspoke. You may not have to have an exact. It may be enough to have a conserved. Okay, so as an example, here's a query. This is the sequence that you submit to the Rosetta algorithm. It breaks it up into fragments. So we'll have 3 residue fragments, KBF, VFG, FGR, GCR, and so forth, and then 9 residue fragments. 9 residue fragments. A fragment consists of a sequence along with a set of torsion angles. Where do you get the set of torsion angles? From known protein structures. That's where you get the set of torsion angles. You guys understand when I talk about torsion angles for proteins? You guys are mostly senior biology majors know about torsion angles. And you've had a lot of chemistry too. Biochemistry? Yeah. Okay, so you assemble these structures, these fragments. So you have a fragment library. What do you do with them? And again, you may have different sets of torsion angles for GRC with it. So you may have several GRC. Okay, got it? So we have this big pile of fragments. Now, do random fragment insertion. Okay? So I'll just pick a bunch of fragments at random. Okay? And I'll probably start with the 9 segment fragments. And once I get a good solution with the 9 segment fragments, then I can go in and start making substitutions with the 3 segment fragments, sort of tuning it up. Okay. So let's say that you pick some fragments that cover the query sequence completely. You pick a set of fragments along with the torsion angles, and that gives you a candidate structure. Okay? Now, it could be anything. Then you start making substitutions. All right? So let's say you have a segment here that has one set of torsion angles for this segment, and you have another candidate, and you substitute it here, and you see that the set of torsion angles for this fragment causes this piece to flip over. So that it goes like that rather than like this. Okay? So you make a substitution at random, and you get another structure. Now you need to score the structure. Did the structure improve? If the score improves, then the insertion is kept. If the score gets worse, the insertion may be kept depending on a parameter which you could call temperature. It's not really a temperature. But this technique, whenever you're doing a search like this, there's a technique called simulated annealing. Okay, simulated annealing, in which you have a parameter that you put very high, like annealing a piece of metal. You have a parameter that you set very high, which you can call the temperature. Set that parameter high, and then when you do a substitution, if the score doesn't improve, you use that parameter to calculate whether or not you're going to keep the substitution, even though it didn't improve the score. And then as you go along, as you move along with the simulation, you lower that parameter, which is equivalent to lowering the temperature. What it does is it keeps you from getting trapped in local minimum. Okay? Imagine that someone said, all right, go over here to the Palouse, this really hilly area north of us, and find the lowest point by walking around. Okay? And so what would you do? You start somewhere and you take a step and you say, did I go down or up? I went down. Okay, I'm going to keep going down. Okay? And you keep walking, and as long as you go down, you keep that step. But then you take a step and you go up. And so you say, I'm not going to take that step. Well, no, because if that was your only rule, that when you take a step, if you go down, you keep it. If you go up, you throw that step away. If that was your only rule, you get stuck in a local minimum. Okay? So what you say is, if I take a step up, I will keep it depending on this parameter. So what that allows you to do is work yourself out of local minimum. Okay? But you keep lowering that parameter until you won't. If you're at a minimum, you'll stay there. So you have a better chance of finding a global minimum and not get stuck in a local minimum. Okay? So this technique of not throwing an insertion away if the score gets worse will allow you to hopefully avoid the local minima in the score. If the low score is a good score, or local maximums. How do you score? Well, you give an environmental score. If these residues happen to be hydrophobic, Then if they're buried inside the protein, that structure is rewarded. So burying hydrophobic side chains inside the protein is a good, gives you a good score. Okay? Hair scores. Rewarding energetically favorable residue-residue interactions. So if your structure brings together two residues that form a bond, say a hydrogen bond or say a disulfide bond, okay, that'll lower the overall energy, so you give the formation of those bonds a high score. So that's how you could get a high score. For example, if you have two beta strands forming a beta sheet, you get a bunch of hydrogen bonds. And that's how you get a high score if it's possible to form a disulfide bond. Okay? We always want disulfide bonds, right? Disulfide bonds are very strong and they help stabilize the overall protein. So if you get a disulfide bond, that gives you a very good score. So if you can get a structure where all of the sulfurs are bonded together, hey, and that's like a candidate. So you have a score. And when you finally finish doing substitutions, and you finally finish, you've got the best score, then typically the output of Rosetta is a set of, say, 10 different models ranked by score. Okay? And then you have to come in and analyze which model might be useful. Human intervention is required at that time. Or you can just take the top score. That's what I showed you. I chose the top scoring models. Okay. All right. Now I want to talk to you about something else quickly, just the last 5 minutes, just an overview. Any questions so far? Homology model. Yeah, homology. So here are the steps in homology modeling. You identify homologs, that is, proteins of known structure with similar sequences. Okay? That's your initial alignment. Then you can execute some procedures that try to improve the alignment. Sometimes you'll have gaps in the alignment. Okay? You've got to do something with the structure in those gaps. Okay? And so there are procedures you can go through to improve the alignment, and that gives you the backbone, the basic backbone. Then, when you have these gaps, you can connect across the gaps with loop, that's called loop modeling. And then you can add the side chains, all right, and adjust the conformations of the side chains until you have a good score, typically a low give-free energy when you adjust the side chain. Then you can refine the model using a molecular dynamics code. And then the last thing is to validate it. That is the predicted model, does the predicted model look like a natural protein? In what sense? Well, does your predicted model have two atoms sitting in the same location? That would be very bad. Or is the distribution of torsion angles typical for a protein? Okay? There's a program that I use for protein structure validation called ProCheck. Okay? And you can submit a structure to ProCheck and it'll give you statistics for that structure. Okay? it'll tell you if there's any positional conflicts. It'll say, are there any anomalous sets of anomalous torsion angles, stuff like that. Okay. So that's how you do validation. You can program that as a project. Okay, so we start with finding a template. So we want blast or side blast, and we get some candidate homologs. So here's our query sequence, starting here, and it's continued here. So this is continued here and here. And here is a candidate. And it does the alignment. When it does the alignment, when it does the alignment, it shows where there's an exact match, end to end, G to G, and then the plus shows where there are conserved matches. And then we have gaps. Gaps show up too, so we can insert gaps. And then it gives you statistics. Identities. There are 146 residues in the query, and 32 residues, 22% are exact match, 42% are conserved differences. You know what I mean by conserved differences? You replace an acid with an acid, you replace a homophobic with a homophobic, and so on. Okay? Now, should you proceed? Should you proceed with that template? And here's a rule of thumb in graphical form. Let's see, we had 142 residues, and we had 22% identical residues. And that puts us here. So it says you could proceed, but don't count on getting anything worthwhile. If you're up here, it's a good idea to proceed. If you're down here, then you don't have a good enough match. Okay. Once you've decided on a template, then you need to score the alignment. And here are the amino acids here. Is the matrix of amino acids, and it's going to be symmetrical about this axis. But it tells you that if you substitute an A for an M, then that gives you a score of 0. If you substitute an A for an L, that gives you a score of -1. Okay. What was that substitution we had for LMCA? It was E for V. Yeah. Let's just look that one up. -1. Okay, that's a -1. If you have an exact, if the homolog is exact, in other words, I have a T for a T, and that gives you a +5. If you get a P for a P, that's really important. It gives you a +8. Why would proline be so important? If you have a proline in the same position, why might that be important? What's that? That's right. Isn't it the only naturally occurring amino acid that is, the side chain is connected in 2 locations? That makes it stiff, okay? And so you get more or less a fixed turning angle when you have a proline. Yeah, so if you get a proline for a proline, that's sort of an anchor for the structure, because you have a fixed set of torsion angles. Just because the side chain is connected in 2 places along that. Okay, so you come up with a score. You have to deal with the gaps, and this shows, this graph shows why this substitution is better than this one as far as the gaps are concerned. And I'm going to have to leave it there. But you go on then and to score have to do something with the gaps, the structure of the gaps, and then something with the side chains, and then you refine it by perhaps running a molecular dynamics code on it. Two popular molecular dynamics code are one codes called NAMD and GROMAX. We use GROMAX in our recent work. And then you do structure validations, and you can use ProCheck or what if server to tell you if your structure looks like a real protein, has the features of what you would expect in an active protein. So I'm going to make these slides available if you want to look at them, and I appreciate you taking the time to listen. Thank you very much.
Thank you very much.